Thank you. It did that before too. That's frustrating. So here's the deal. When you have a model that looks like this, what you have to understand is what's going to happen to it. So it looks like it starts down here at 0-ish, yes? Starting down here at 0-ish. And then it's beginning to curve, like almost exponentially like this, yes? And then it's beginning to turn like this. What's going to happen?
It's going to level off.
As a vote for it's going to level off. Does that make sense? Yes, second, it's going to level off. Why does that make sense in the context of our little problem here?
Because
Because we have a fixed number of people in this room. It can't keep growing. And it doesn't make sense that it should drop off. Maybe past the point as people start getting healthier, it drops off. But if we're talking about modeling the infection rate of this virus, it's not going to level off. It's not going to level off. So this guy is going to whoa, it's going to do that. So when you look about the exponential models, they have a level off line too, but only one of them. This one has two level off lines. It's got the initial level off line. These are called asymptotes mathematically. And then it's got a secondary one on top. Like that. This is very, very handy. Very, very handy when you talk about something that's growing exponentially and then can't keep the exponential growth going because it runs out of resources for whatever. This is where your model would come in, Andrew. You go ahead, make 5% more per year, but give it a top limit. We can't expect you guys to sell $8,000 per day. But an exponential model will eventually get there. This won't. You can put a cap. So you can force a cap at whatever a realistic number would be and then exponentially grow up to a point and then level off and get tired, if you will, and then approach it. Yes? Fair enough? Now, how do we model this? Well, this model is called a logistic model. It's called a logistic model. Logistic. But just like the exponential, it's kind of twitchy with what it wants data-wise. Check this out. Everybody, go find that. It's in the same place all the other regressions are, but there's no REG word after it. So stat, calc, I think it's near the bottom. Yeah. Yep, it's a couple below X-ray. So grab that one. Yep, B on mine as well. Grab that one.
Which
and
one?
logistic.
Oh, okay, B.
Mm-hmm.
Right.
It's letter choice B.
Yeah.
Make sure you put your Y1 after it like you always do.
I'm still getting an error.
And then try to understand why. Oops, hold tight. I have to fix something real quick.
Oh, I got an error.
You good, you should. I fixed it, which I didn't get the error. Okay. There. Error domain, just like you guys are getting. This is the same error you get with exponential modeling. Why? Because you have a Y value of 0.
So we need to take those.
We have to take that point out. Take out the point that has a Y value of 0. In that case, 0, 0. In the case of this one, 0, 0. So we quit, we go back to the stat editor, and remove the 0, 0 in the beginning. Starting at 1, 1 will be fine enough. It'll get that as it can't zero out. It just gets close to zeroing out. So let's remove that, and remove that. This is where you gotta be careful with your div error too. How do you do that? Just the DEL button, put it on top and press DEL. Yep. Everybody follow that? DEL, good. Now quit back out. Try it again. This one will take it some time. It will take it some time. It's thinking. It's thinking very well, actually. Okay.
Where was L1 again?
Say that again.
Why doesn't work?
Why?
Logistic.
Take the zeros out.
The Z.
No, I got I forgot how you do Y1.
Get your booklet out, brother. Slap me in the face. Give you a gift.
That's what I said. I was like,
Now, these numbers are extraordinarily interesting. These numbers are extraordinarily interesting, and I don't want you to worry about them very much. I will tell you this, though. This little guy right here, this is approximately how many people were in the room at the beginning of the experiment. That's what that number will get closer to with more and more precise data. Everything else is interesting, too. It all has interest rates and all kinds of rates of compound. I'm not so much interested in that. Just press graph and check out how well it fits the data. It captures the exponential in the beginning, and then it captures the turn at the end. It's kind of like Usain Bolt. It's kind of like Usain Bolt's data. You'll see this when you start looking at Usain's data more carefully, as it has this cool shimmy right here. That's called an inflection point. That means the curve goes from going like this to going like that. None of the curves we've looked at so far have had those. Lines don't have them. Parabolas don't have them because they're always curving the same way. Imagine water. Imagine water getting caught or running off of something. Here, water would be caught. Here, water would run off. Parabolas always either catch or run off. They don't have both. Does that make sense? Exponentials, same exact thing. They're always catching water. These guys have this cool shift of gears. And that is right when the resources start getting taxed. And the virus can't infect exponential like it's trying to do. Which means its rate of infection has to slow down. I mentioned this in your out-of-class exam because that means the acceleration is changing. We've talked about acceleration before in here, me and my bike. My bike is constant acceleration. As long as I'm rolling down the hill, I'm picking up speed. The speed of this virus infection is slowing, though, on time, and eventually it levels off, and there is no speed of infection anymore because we're infecting more people. Does that make sense? Does that make sense? So this is a way you can kind of model, should we be terrified about this meningitis scare? I don't know. Let's get the data to me. Let's model it in class together. Give it whatever data you can.
Yeah, because eventually it'll just hit everybody.
That's not true if it's not behaving like this. We can check the data and see if it actually fits this model. I don't know. I have to get the data to see. Now that might be trickier. That might be easier said than done, right, Guy? It might be easier said than done, as it often is. Getting raw data can be kind of tricky.
Yeah, and what we get on the news is an outline of the real story.
Exactly. It might not be time period data, that kind of stuff. So, okie doke. So there you go. So we'll call it a day. So for Wednesday, quadratic and linear modeling, we'll do questions on these guys on Monday. Cool? And then we'll get the probability again on Wednesday. So every time we have left on Wednesday, we'll get the probability a little bit. A little bit. Just look at activity to get you guys started thinking about it. Okay, doke? Did that turn off again or is it still recording?
It's still recording.
Okay. So I don't know what's going on. Let me see what the battery says.